Ladies and gentlemen, thank you for the honor of speaking to you today. My mission is to make you aware of a new distillation technique that can bring benefits to a wide range of industrial applications. To make the best of time, I will restrict the discussion to applications in which the volatile material is mainly water and the non-volatile material is temperature sensitive. You will be able to extrapolate the material later on at your leisure. Most of what I present today can be found in some form on the website www.passthroughdistillation.com. Here is a roadmap for today's presentation. Notice that I have chosen to put pilot plant work near the start. The idea here is to heighten your interest by showing you a working prototype. We are not merely discussing a theory. But first of all, the background. I am a mechanical engineer who has spent his career in a family business called Fielding Chemical Technologies, located near Toronto, Canada. Fielding was founded in 1955 and is now one of North America's foremost recyclers of solvents and other industrial wastes. Lacking the capital resources to buy new equipment, the company has become good at developing and building its own processes and equipment. 15 years ago, we developed a technically elegant prevaporation technology to remove water from distilled solvents. A spin-off company named Drystill was created in 2006 to market that technology into other areas of industry. Not long afterwards, Drystill made discoveries in the realm of pass-through distillation and decided to abandon prevaporation in favor of the opportunities that I will tell you about this morning. As promised, here is the Drystill pilot plant, sponsored by Fielding in the belief that the technology will make a breakthrough in the treatment of watery industrial wastes that are too high in solids to be sent to bug ponds and too low in fuel value to be economically incinerated. The video you are watching shows Drystill's prototype SAM in operation. SAM is an acronym for Stripper Absorber Module. The blue liquid is water with a little dye in it. The yellow liquid is concentrated lithium bromide solution. Water is being evaporated in the blue section and absorbed in the yellow section. The graph shows a segment of the saturated steam tables, showing the intended range of operation. Here is a slide showing the layout of the pilot plant. The nominal production capacity is 45 kilograms per hour of distilled water. Here are some details of the prototype SAM itself. 100 heat pipes are used to transmit the heat released by the absorption process into the evaporator. This slide shows what the pilot plant does. The blue water in the feed tote circulates through the SAM's evaporator compartment, while the brine circulates through SAM's absorption section, and then through a desorber, which is a single effect distillation device. We feel confident that pass-through distillation can make contributions to many industries under these important headings. If I have your interest, I would like to lead you through a thought experiment. Our apparatus consists of two vessels containing nothing but liquid and gaseous water. The two vessels are connected by a vapor duct. Circulation pumps and spray nozzles ensure that within each vessel the phases are in thermal equilibrium. Each vessel is also equipped with a heat exchange coil that can be used either to heat or to chill the contents. If we allow the two vessels to arrive at the same temperature, their pressures will be exactly equal and the net flow of gas will be zero. If we slowly add heat to the left side while removing heat at the same rate from the right side, we will cause gas to flow from left to right. The apparatus is completely symmetrical. So if we add heat to the right side and remove it from the left, gas flows from right to left. We lose this symmetry if we now add salt to the left-hand vessel. In order to balance the vapor pressures in the two vessels, we must raise the temperature in the left-hand vessel by an amount known as the boiling point elevation, or BPE. As long as we are careful to maintain that temperature differential, The pressures in the two vessels will be equal and the gas flow will be zero. Now, if we add heat to the vessel containing the brine and remove heat at the same rate from the vessel containing pure water, then there will be some evaporation in the first vessel. Vapor will flow from left to right and will condense. The left-hand vessel may be called a spray evaporator, and the right-hand vessel a direct contact condenser. This process is distillation as we all know it. It follows the familiar pattern of having a hot evaporator and a cool condenser. If we now reverse the heating and cooling coils, taking care to maintain the boiling point elevation, we would be asking water to boil in the right-hand vessel and move to the left-hand vessel where it would turn back into the liquid state and become a part of the circulating brine. But can that really happen? Note that this process would involve a net flow of heat from a lower temperature to a higher temperature. This is a direct violation of the rule, heat flows from hot to cold. Well, friends, I am here to tell you that this reverse distillation process can and does happen. It is called gas absorption. The rule it appears to violate is the same one that tells us that water always flows downhill. True, it will always flow downhill spontaneously, but we all know that water will flow uphill if induced by a pump. Similarly, heat will flow from cold to hot if induced by a heat pump. So where is the heat pump? Nothing here looks very much like a heat pump. That is until we add some equipment to make it operate continuously. You see, as the salt solution absorbs water vapor, it becomes more dilute. We must add a device to reconcentrate the brine by removing the absorbed water. This can be accomplished by distillation. A portion of the dilute brine enters a still and is separated into a stream of product water and concentrated brine. The concentrated brine is put back into the absorber vessel, and the water product can be sent back to the evaporator to complete the water circuit. Those skilled in the art of heat pumps will recognize this as an absorption chiller. It was invented 150 years ago in France and is now in service all over the world, providing air conditioning in large buildings. Lithium bromide is the most commonly used salt in the brine. The evaporator typically operates at an absolute pressure of 6 torr and a temperature of 5 degrees Celsius. The evaporator is the sink for the air conditioning load. The absorber also operates at 6 torr but at a much higher temperature, typically 40 degrees Celsius. At this temperature, heat can be removed from the absorber with ordinary plant cooling water, furnished by evaporative cooling towers. So our little thought experiment has led us to the rediscovery of the absorption chiller. But I would like to take us one step backwards, before we closed the water circuit. What if we fed the evaporator with an externally supplied stream of slightly contaminated water, removed a bottom stream from the evaporator, and took a stream of distilled water as product from the condenser? What would you call such a process? It involves evaporation through the addition of heat, condensation through the removal of heat, so it meets the general definition of distillation. But along the way, the distillate passed through an intermediate fluid, the absorption brine. Now this suggests a name for the process, pass-through distillation, and it is the name that we will use for the remainder of this presentation. Let us now see how pass-through distillation compares with ordinary distillation with respect to temperatures. In this chart, important temperatures are shown for a particular plant operating a single-effect distillation. The maximum available temperature from the steam supply is 230 C. The cooling water has a nominal temperature of 30 C. The product being distilled is temperature sensitive, and a limit of 85 C has been set for the process. The temperature difference between the 85 degrees C subatmospheric steam and the 30 degrees C cooling water is shared between the heater and the condenser. If they are balanced in size, each will have a delta T of 27.5 Celsius degrees. Distillation may be carried out using multiple chambers with progressively lower temperatures and pressures. This is known as multiple effect distillation, or MED. Here is a two-effect or double effect unit. The high pressure vessel is heated by plant steam, while the low pressure vessel is heated by the vapors generated in that first vessel. The advantage of this arrangement is that the heat from the plant steam gets used twice. The energy cost per kilogram of distillate is cut roughly in half. Here is what a three-effect installation looks like. Energy is used 3 times at progressively lower temperatures and pressures. Here's the temperature map for single, double, triple, and quadruple effect units operating in the environment shown earlier. As each effect is added, the delta T available to drive the heat becomes smaller, from 27.5 degrees to 18.3 degrees to 13.8 degrees to 11 degrees. These numbers are based on the assumption that the volatiles boil and condense at the same temperature. But this is rarely the case in industry. Here is what the temperature map looks like if there is a boiling point elevation involved. The delta T's become very skinny. Engineers compensate by making heat exchange surface areas very large, which means high capital cost. In pass-through distillation, the absorbent brine may be regenerated by multiple effect distillation. All the temperature-sensitive material was left behind in the evaporator, so the temperature constraints that affect conventional distillation do not apply. Here is a 4-effect desorber making full use of the 200-degree spread between the steam and the cooling water. Much of this temperature space is used up by boiling point elevation. Nevertheless, each of the 5 heat exchangers gets a generous 16-degree delta T. Now suppose a great drought afflicted a particular area and authorities banned the use of evaporative cooling. All industrial facilities would then be forced to resort to direct air cooling using fin fans. This would raise the nominal temperature of the plant heat sink from 30 degrees C to 50 degrees. This slide compares the effect the change would have on different distillation arrangements. For the desorber of pass-through distillation plant, delta T's drop from 16 degrees to 12 degrees, a 25% impact. The conventional distillation units are affected much more severely. And if there is a boiling point elevation involved, delta T's may become so small that multiple effect distillation is not feasible. In many parts of the world, drought is a present reality, and restrictions on evaporative cooling already exist. In these areas, pass-through distillation may become the only economic means of distillation where highly temperature-sensitive materials are involved. We have learned that the desorber may operate with a very high temperature first effect, that it can have up to 4 effects, and that it may be air-cooled. But to operate at all, it needs a vacuum pump. An absorption chiller does not have one because it is a closed system. But pass-through distillation is an open system. Dissolved gases in the feed must be continually removed in order to maintain the desired operating pressure. The size of the vacuum pump must be matched to the rate of incoming non-condensable gases and to the system's operating pressure. Vacuum pumps, after all, are volumetric devices, and the volume of gases vary inversely with the absolute pressure. If you are operating at 50 torr and decide that you want to change to 25 torr, the size of the vacuum pump must be doubled. Let's keep this in mind as we move on to the topic of evaporator temperature. In pass-through distillation, evaporator temperature is a matter of design choice. 3 possible choices are shown here. all are valid. The steam and cooling water temperatures have no importance in this choice. The designer of a pass-through distillation facility has freedom of choice that is not enjoyed by a designer of conventional equipment. For ordinary stills, it is the temperature of the cooling water that determines the lowest possible operating pressure in the evaporator. This is because all condensable gases must be condensed upstream of the vacuum pump. If the condenser fails to condense everything condensable, then the vacuum pump will be overwhelmed by product vapors. I learned this the hard way when I worked on the evaporation project that I mentioned earlier. When we worked with membranes in the lab, our vacuum pump had a liquid nitrogen cold trap in front of it, so we could operate at very low pressures indeed. 10 to the minus 2 torr was no problem. But when we scaled up to a pilot plant, we used a refrigerated condenser, and it was very troublesome. We couldn't control it properly. Either it would become too cold and freeze up, or it would become too warm and allow uncondensed vapors to flood the vacuum pump. We were working with isopropyl alcohol, and when the alcohol got into the vacuum pump, it would thin the oil and eventually cause the pump to fail. In desperation, we installed a scrubbing system in front of the vacuum pump instead of the refrigerated condenser, and it was a spectacular success. The lithium bromide brine absorbed both water and alcohol, allowing air and other non-condensables to pass. You will notice that our vacuum system bears a very strong resemblance to the pass-through distillation arrangements that we have been discussing. We ran the evaporation plant for 4 years, during which time we produced over 1 million liters of dry isopropyl alcohol from feedstock containing 14% water. This experience has given us a lot of confidence in pursuing our pass-through distillation pilot plant. Now I would like to share with you the contribution that dry still has made to the field of pass-through distillation. Here is a block diagram of pass-through distillation with the evaporator and the absorber shown as 2 separate vessels connected by a vapor duct. But since the 2 vessels operate at the same pressure, they may be combined into a single shell. Manufacturers of absorption chillers do exactly that. Here is a schematic of a commercial absorption chiller. The lower vessel is divided by a wall that separates the evaporator section on the right from the absorber section on the left. The evaporator section contains a heat exchange coil that brings low-grade heat into the vessel, while the absorber section has a set of heat exchange coils that remove heat from the absorber. The 2 coils handle roughly the same amount of heat, that is, the latent heat of evaporation of the water vapor passing from the evaporator to the absorber. Dry still has adapted this concept to an open system through the invention of the SAM, a prototype of which you saw in operation at the start of this presentation. In a 2-dimensional schematic, we show the SAM in this form. Vapors generated in the evaporator are routed to the bottom of the absorber section, so that in order to reach the vacuum pump, they must travel counter-current to the falling absorbent fluid, maximizing the opportunity for absorption to occur. No heat exchange coils are involved. The warm absorber conveys its heat to the cool evaporator by means of heat pipes. For the purpose of this presentation, we may consider heat pipes as superconductors of heat. The modern heat pipe was developed in the 1960s by NASA for the space program. Heat pipes have been appearing in consumer products in recent years, most notably in laptop computers, as a way to conduct heat away from the processor chip. Although the chemical industry has not yet made great use of heat pipes, they are ideal for the needs of pass-through distillation. Our prototype SAM does not use the double baffle construction shown here. Building a 3-dimensional object affords more freedom than making a 2-dimensional sketch. But a SAM could be made so that in cross-section it would appear exactly as shown in this schematic. Here is a 3D rendering of such a SAM, showing how it would come apart for cleaning. The heat pipe bundle is a completely independent subassembly that slides in and out unencumbered by any connecting pipe work. This simplicity will make pass-through distillation attractive to those concerned with capital cost and ease of maintenance. But the most important message of this presentation is that pass-through distillation saves energy by making MED available to distillations involving temperature-sensitive materials. It does not by any means make all other forms of distillation obsolete, but it belongs in the toolbox of every chemical engineer and process designer. Thank you for your kind attention.